Ladies and gentlemen, welcome to the third talk of this session. The speaker is Shao-Jiang Wang from Institute of Theoretical Physics, Chinese Academy of Science. He is an expert in cosmology and is going to talk on cosmological tensions and implications for a non-minimally coupled dark matter with dark energy for the next hour. Please join me in welcoming Shao-Jiang Wang.
Thank you very much for the invitation. And today I'm very happy to talk about our several recent work on the cosmological tension, including the Hubble tension and the recent implication for the DC dark energy. Okay, so I assume that most of the people in this room are not working on the cosmology, and so I will introduce a little about a background on the cosmology. So as we know that the modern cosmology is initiated from the cosmological principle by Einstein that our universe is spatially homogeneous and isotropic above some certain scale. So this scale is approximately 100 megaparsec. So to determine this scale from the data, it's a little bit tricky. One way to determine this homogeneous scale is to count the number of the galaxies within a certain sphere. So if the total number of the galaxies within a certain scale is increasing with cubic power of the radius of that scale, then we can think that that scale is the homogeneous scale. And so we can see that with increasing radius of this sphere, the power is reaching approximately 3 at this 17 megaparsecs per edge. So here the edge is the dimension is Hubble constant divided by 100. So this is 0.7. So this scale is approximately 100 megaparsecs. So this is the scale for the homogeneity. So about this scale, our universe is homogeneous. Then we can use a homogeneous matrix to describe our universe. But below this scale, our universe is a homogeneous background plus some perturbation until some nonlinear scale. So below this nonlinear scale, we have to run the numerical simulation to actually determine the evolution of galaxies. So back to the last century, we know that there's a 3 observational facts that help us to build this hot Big Bang picture. So one is the Hubble expansion law, the other is the Big Bang nucleosynthesis, and the third one is the cosmic microwave background radiation. So they all point to the fact that our universe is initiated from a hot, dense singularity, but we know that singularity is not popular, so it's not welcome. So we need to we need some early universe inflationary error to smooth out the inhomogeneity and also give us the hot Big Bang view as the preheating error after inflation. So this is the current picture of our universe that we are born from unknown states, followed by an inflation, and after inflation we have a reheating, and this reheating resembles the traditional picture of hot Big Bang. And after hot Big Bang, we have this early radiation dominant error and matter dominant error, and also our current dark energy dominant error. So since the last century, we have many precision cosmological observation from the CMB, and also the local large-scale structure survey, and also the distance large-scale structure survey, and also the local distance ladder measurement. So for all this precision cosmology, we have established a concordant cosmology. So from these 3 special facts, we identify the fraction of dark energy and also the fraction of matter. So this is the current recipe of our universe. But there's So this is the current recipe of our universe described by this FRW equation that the Hubble expansion rate is given by these three components. But we know that there's three problems for this equation. First of all, the matter consists of the baryon and also the Kodak matter, and we don't know the Kodak matter. And also we don't know the baryon symmetry for the baryon component. And then there's a cosmological constant problem. Then is a cosmological coincident problem that the current fraction of matter and the cosmological constant is approximately at the same magnitude, and we don't know why, because they redshift rather differently along the history of the universe, but by unknown reason, they are coincident at the present day. This is the redshift. The redshift. Yeah, you can think of as some label of the time. Okay. And then there's a cosmological constant problem that observes the energy density of the cosmological constants is at the same order of the Hubble constants. And we know that Hubble constants measure in the Planck unit is very small number. So we don't know why this lambda is so small. So there's three problems for this FRW equation. Now, this is the standard cosmological model for our current universe. So as I say, we are born from some unknown initial condition. So this may require some quantum gravity scenario to give us the answer. And then we are followed by inflation, which is the early time acceleration. During the inflation, we generate the quantum fluctuation, which re-enter our Hubble horizon at a later time as this radiation fluctuation and also the matter fluctuation. The radiation fluctuation is imprinted at the last scattering surface. So this is what we measure by the cosmic microwave diagram. That's the temperature fluctuation is 1 to 200,000. So, and then the matter fluctuation later clustering into a galaxy and other large-scale structure. So this is mainly dominated by the dark matter dynamics. And our current universe, we don't know the baryon symmetry, and also we don't know the late time acceleration, whether it is caused by dark energy or vacuum energy, or even its fluctuation. So this may also require the quantum gravity to answer. So now, let's look at the one important parameter in our current universe, which is the Hubble constant. So this is a cartoon picture of our universe expanding, and we can view it as a two-dimensional sphere. So this is actually a three-dimensional sphere. So we can simplify this picture in the in this S1 ring. So there's two distant galaxies. During the expansion, the co-moving coordinates. So in this picture, the co-moving coordinate is just the angle between these two galaxies. When the universe is expanding, which is equivalent to the increase in radius. So the co-moving distance does not change, but the physical distance is changing with respect to the scale factor. So we can measure the distance of the two galaxies, and then we can measure the velocity of this physical distance. It is proportional to the physical distance times a Hubble parameter. And our current Hubble parameter is called the Hubble constant. So in observation, we just measure the redshift between these two galaxies, and it is approximately equal to the recessional velocity. And by dividing the recessional velocity with the distance, we can measure this Hubble constant. Okay. There's two ways to measure these Hubble constants, one from our early universe and then the other from our late universe. So in the early universe, we have this CMB measurement of the sun horizon. And also we have to assume that standard model is valid between the Big Bang nucleogenesis, between the Big Bang nucleogenesis and the CMB. And then we assume that in this region, the lambda CDM model is valid. Then there's a late time measurement. So we have to use this local distance ladder to measure Hubble constant. The way to measure it is that we have this Hubble flow supernova between these redshifts, and then you have to using local distance ladder. For example, this is a sphere in our Milky Way and other nearby galaxies. To use the sphere, we can measure the sphere in some galaxies with also this supernova host. And then we measure the absolute magnitude of the supernova in this host. And then when we use this calibrate supernova to calibrate the Hubble flow supernova, then we assume that the model between this redshift is lambda CDM model. Then you extrapolate to our current time, you measure this Hubble constant to be 73. But the early universe will measure the Hubble constants as 16.7. So there's a tension between these two measurements. So let's look at the early measurement. The early measurement is to fit the CMB data with this 6-parameter based model. So here, the lambda CDM model can be described by this red part, the 6th red part, as the 6th parameter. So these two parameters characterize our primordial fluctuation. And these two parameters characterize our physical energy contents of the matter. And for the radiation part, it is determined by the CMB temperature and also the standard model particle physics. And there's another two parameter. One is the Thomson scattering orbital depth. So this will give us the redshift to the last scattering surface. And then there's a characteristic angular size of the first angle in the CMB spectrum. So this quantity is measured to the very high precision. So every red part is known, and or every green part is known, but the red part is unknown. So you can fit all the red parameter with the CMB, and then you can determine this blue part. Now, once this blue part is determined, you can take the scale factor to be 1, which is our current universe. Then you can determine the Hubble constant from the CMB fitted by the lambda CDM model. Now, the lambda CDM model fitted with CMB has very consistent measurement for the Hubble constant. Here is the Planck measurement of the Hubble constant. But if you don't use the Planck CMB data, you can use other ground-based CMB measurement. You can see that they are very consistent for the measurement of Hubble constants. Even if we don't use any CMB data, for example, we can use this baryon acoustics oscillation plus the Big Bang nucleosynthesis. You can also find that their combination is consistent with the CMB results. So the early measurements, they all point to 16.7 value for the Hubble constants. Now let's look at the late measurements. The late measurements consists of this local distance ladder. So I explained before that we have some sphere in our nearby galaxies, and so we can measure the distance of this sphere to measure the absolute magnitude of the sphere in the second ladder, and use this sphere to measure the absolute magnitude of the supernova in this distant ladder, and then we use this calibrate the supernova to calibrate the supernova in the third distant ladder. DEB is the detached elliptical binary. So binary, this is a special kind of binary that help us to determine. So this is the geometric measurement of the distance nearby our Milky Way galaxies. So there's 3 different kinds of the geometric measurements. Maser is also a special kind of a stellar. So how to determine Hubble constant from these 3 distant ladder? Well, it's very simple. First of all, the supernova in the third distant ladder, they have many number of them. So the statistical systematics is very small, and you can measure the apparent magnitude and also the redshifts of this supernova in the third distant ladder. And you can fit this parameter called the intercept parameter. This intercept parameter is a degenerate parameter of the apparent magnitude of the supernova and also the Hubble constant. So once you fit the supernova in the third distant ladder with this relation, you can determine the intercept value to a very high precision. Now, to determine the Hubble constant, you only need to know the absolute magnitude of the supernova. But we know that we can measure the absolute magnitude of supernova in the second distant ladder, and then we can make one further assumption that the absolute magnitude of the supernova in the second distant ladder does not change when we transit to the third distant ladder, and then you just enter this second distant ladder measurement of the absolute magnitude of the supernova. You can determine the Hubble constant from this local distant ladder. So this is how you determine the Hubble constant from late measurement. Well, there's a major systematics in this measurement, which is this assumption that the supernova does not change its property going from the local universe to the late universe. So there are so many systematics, and as long as the Schultz collaboration has checked, the deviation is within the 1 sigma region. So the measurement is very robust to this systematics. And also, people have used this JWST telescope to calibrate the previous results, and the result is consistent with earlier measurements. So the Hubble constant is still very stable. So even if you don't use any information from the third distant ladder, you can solely use the first two distant ladder measurement to measure the Hubble constant. Here you can use the distance modulus of the sphere in the second ladder, and then also the redshifts in the second ladder. You can directly measure the Hubble constant from the first two distant ladder, and the result is consistent with all three ladder uses. So the results are consistent with the previous result. So we still have this Hubble constant tension between these two measurements. So sorry, I have to speed up. So usually in cosmology, we call 2 or 3 sigma difference as discrepancy, and 3 to 4 sigma difference as a tension. But now we have 5 sigma difference between the early measurement from CMB and the early measurement from CMB, and also the late measurement from the local distant ladder, and this is 5 sigma. Now it's larger than 5 sigma, so we are really facing a crisis. And the Hubble tension is also regarded as an early and late tension between our early universe and our late universe. As you can see, all different kind of early universe measurements is systematically shifted from the local measurements. So there may be a systematic reason that why these two kind of measurements are different with each other. So this is the background measurement for the Hubble constant, but also we have this perturbative measurement of the matter perturbation at a linear scale. So the early measurements of this quantity is also systematically shaped from the late measurement. So we may face in this early and late tension. So now this is the outline of my talk today. I will first of all talk about the early universe and late universe to highlight that as the sound horizon tension, the matter perturbation tension, and also the absolute magnitude tension. Then I will briefly mention our current result, that's the DESI measurement for the dark energy. But I will show that this result is highly biased, and what we really needed is some late time modified gravity. Then I will highlight our result that what kind of modified gravity we are expecting, and this might relate to the picture of some string theory. Okay, so let's look at the early measurement, the early solution for the Hubble tension. So if the Hubble tension is caused by a modified early universe, then what we expect that we don't change anything around the late universe. It's still described by the lambda CDM model. But the early universe should be changed because that's if the hypertension is caused by modification to the early universe, then you will see that the sound horizon between the early and late universe are different. The early universe prefer the sound horizon is 177 megaparsec, but late universe, if we extrapolate at higher redshift to the CMB, it is 136 megaparsecs. So you have to modify somehow the early universe to shrink the sound horizon to match our late universe value. How to do that? Well, the most simple way to do that is to insert some early dark energy. The early dark energy is negligible in the early universe, but since his energy density is not diluted in the early universe, so sooner or later their energy will account for a significant part of our early universe energy. So when the fraction of early dark energy is like say 10% of the total energy at that time, and they will significantly shrink the sound horizon. And then after he shrink the sound horizon, you need this early dark energy to dilute it very fast, not to interrupt the CMB measurement. Then you will find a Hubble constant larger than the original one. But in this picture, you will face some very serious problem. For example, in this model, it will predict the scalar spectral index is very close to 1. So you have to also modify our primordial universe for the inflationary model. It's very trivial thing to do. It's a very non-trivial thing to do. Second of all, it will also cause the sound horizon tension. So this kind of modification can ease this sound horizon tension, but at the same time, it will worsen this matter fluctuation tension. So you have to also modify the late universe to be consistent. So basically, although you are start out to modify the early universe, but in the end, you have to modify our universe from the very beginning to the very end. The price is very high. So here I briefly mentioned that's why the early modification will worsen this matter fluctuation tension. So to modify the early universe, you have to shrink sound horizon. There's two ways to do that. One is to modify the early time expansion history. The other one is to modify the recombination history. To do that, we can inject some new energy to enlarge the early expansion rate, and also we can advance in the recombination to modify the early recombination history. But both of these two modifications will have some consequences. For example, if you inject some new energy, it just gets the early expansion rate to be faster, so it will suppress more the matter perturbation growth. So you might need a larger matter fraction to match the observed large-scale structure. And also, if you advance in the recombination era, then the time for the matter perturbation to grow is becoming much shorter. So you have to also require the larger matter fraction to match the observed large-scale structure. So in the end, you will have a larger SA to deviate it from the CMB measurement. So it's not a good thing. The second is that as I mentioned, that all these early universe modification will enlarge this scalar spectral index to be very close to 1. So there's some example of the early dark free model. The measurement is very close to 1, but our current measurement is around 0.96 and 78, so around here. But it will require this NS very much close to 1. So in order to do that, you have to modify the inflationary model. Here is an example of our work. So here you have to add this derivative coupling between the gravity and the scalar field. This kind of coupling is inherent from the from the heterotic string theory. But in that theory, it requires this coupling constant to be larger than 0. But to fit the data, you need a negative value of this coupling constant. So it is still possible to do that. And also, modify the early universe is not enough, because there's so here is a review paper. It says that due to this observational fact, modify the early universe is not enough to solve all these observational facts. So we still running into an end when you modify the early universe alone. Now let's look at the late universe. So if the hypertension is caused by the late universe, it means that you don't have to change anything in the early universe. You only have to speed up our late universe to expand even faster than the cosmological constant, which means that we may need some phantom transition at the late universe. There's several ways to speed up our late universe acceleration faster than the cosmological constant. So here we can add some phantom dark energy at the late universe to expand faster. So if you only use this BO data, it seems possible that you can have a phantom transition as our local universe. But if you use the supernova data simultaneously, it will constrain this part of expansion to be very close to the lambda CDM model. So in the end, it's not easy to do that. There's another way to speed up our late time acceleration faster than the cosmological constant. The way to do that is that you have to change the Newton constants. The Newton constant will affect the critical mass of the white dwarf to explode to be a supernova. So it will change the absolute magnitude of the supernova to make it to become less bright at long distances. But there are some constraints from the Snowball Earth episodes. This kind of constraint we are forbidden us to change these Newton constants at very late universe. So I just briefly mentioned these things. So it seems impossible to modify the late universe to solve the Hubble tension. Here I present even more general constraint for the late universe. So to do that, we need model-independent parameterization for the late universe. The one way to do that is to use the cosmic age to parameterize the late time evolution. The reason to do that is that the usual way to parameterize the late time expansion, people usually parameterize this Hubble expansion rate directly with the Taylor expansion in terms of the redshift. But it is not very good thing, because you can imagine some exotic dark energy component to change this Hubble parameter very rapidly, and the tidal expansion is not very good enough to capture this feature. So a better way to do that is to parameterize some integration parameter. For example, the cosmic age accumulated from the early universe to the late universe. Even if we have very exotic dark energy component to change the expansion rate very fastly, the accumulated age will change a little bit. So we can expand the cosmic age in terms of the cosmic age divided by our current age. So for the matter dominant error, this combination is just precisely 2/3. With some dark energy, it will deviate from 2/3 with this kind of behavior. So we can parameterize the Hubble expansion rates in terms of these two parameters. So these two parameters will capture almost all of the dark energy at the late time. But in the end, what we show is that even if you use this parameterization for the new physics at late time, the difference between this new physics model with respect to the lambda CDM model is almost negligible. And the Bayes information criteria is also larger than the lambda CDM model by 10. So there's a strong evidence to against any late time new physics beyond this lambda CDM model at late time. So we have done this even better by changing the BLO data from the 3D BLO to the 2D BLO. So this is because that when we measure the BLO in 3D, you actually have to assume a fiducial cosmology to measure the distance. But for the 2D BLO, we only measure the angle of the two galaxies, and this is independent of the cosmology we use. And there's another data called the Cosmological chronometer, and this data is also independent of the cosmology model. So all these kind of three data combination is they are all independent of the cosmology. And then we use this model independent parameterization. Then we will find that the difference between this new physics model with respect to the lambda CDM model is also negligible. So there's a strong evidence to against any new physics beyond the lambda CDM model at a late time. Okay, but you would ask that the recent measurement from the DESI, this is the dark energy spectroscopic instrument. So this is a recent measurement from the large scale structure. They seems to imply that the dark energy is dynamical with respect to the lambda CDM model. So lambda CDM model predicts the dark energy is a constant at this point, but the DESI measurement has a 2 or 3 or even 4 sigma confidence that we have some discrepancy between the dark energy and the lambda CDM model. But BLO is a baryon acoustic oscillation. It's measure the 2-point correlation of the galaxies. So for our current universe, there's a characteristic scale for this 2-point correlation. And there's at a certain scale, this 2-point correlation is larger than the sample with the random distribution. So this is characteristic scale imprint in our expansion of the universe. To measure this scale, you can constrain the cosmological constant to constrain the cosmological model to very high precision. And this is what their measurement. They measure that through this scale, we can measure our late time cosmological model to be deviated from the lambda CDM model more than 2, 3, or 4 sigma way. But what they actually measure is not this 2 parameter in the parameterization of the dark energy. What they measure is actually the phantom crossing redshift. This phantom crossing redshift is around this form, and what they actually measure is this redshift. Away from this redshift, the measurement is not so confident as this red line is the projection of these 2 parameters, and you can see that the width of this parameter is actually larger than the diagonal direction. So actually, you don't measure this 2 parameter to very precise value. What we measure is this diagonal direction to the high precision, and this diagonal direction is actually the redshift for the phantom dark energy to crossing the line of the cosmological constants. Okay, but if you look at these results more carefully, you will find that their result is variant when this BLO data combined to different supernova data. There's 3 different kinds of supernova data. This is the Passen-Prost Unit 3 and dark energy survey year 5 data. And you'll find that there's a discrepancy between this Passen-Prost sample and also the dark energy survey year 5 data. The dark energy survey year 5 data consists of 2 sub-samples. One is the low Z sample, the other is the dark energy survey supernova. And you will find that this intercept quantity measured by these two subsample is different at this redshift. So there's a discrepancy of this AB parameter around this redshift 0.1. But for the Python Pro sample, the measurable value of AB is stable and consistent in all redshifts. So you will see that if you use the lambda CDM model, you will find there's a discrepancy of this AB. So there's an AB tension here. So you might think that this AB tension is not real. Maybe we can change the model to match these two values together inside this dark energy EFI data. For example, we can actually change the model to match these two values at this point. But the very same model will deviate it, will shift away of the value of AB for the Python cross data. So you cannot do both. For example, I show the result with the density-based W0, W8 CDM model. You will find that using the new model, although you can match these two together, but you will shift away for the Python cross data. So you cannot do both. So the reason for the AB tension cannot come from the new cosmological model. So it can only stem from the systematics. So yes, in the low Z supernova data. Yeah, because in the high Z supernova data, these two measurements of the apparent magnitude and the redshift is very stable against any peculiar velocity effects because they are at the high redshift. So the effect is very small. So the only possibility is that there are some unknown systematics in the measurement of the redshift and also apparent magnitude that is highly affected by the peculiar velocity. So you have to correct the low Z data. Low redshift is smaller than 0. Sorry. No, Python pros is okay. You see that for the Python pros is stable. So what I mean by low Z data is this low Z data in the dark energy survey EFI data. Yeah, and it is this data combination give us the largest significance from the lambda CDM model. Okay, so yes. They only done that for the data release 1, but not for data release 2 yet. Yeah. Yeah. Yes. Yes, I agree. Issue with the BLO data too. Yes. 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 I agree. So here I show one possibility to reduce the dark energy significance. So since the low Z data has some unknown systematic, we have to correct it. So there's two ways to this AB tension. First, we admit that AB tension around the 0.1 is real. That means there is a transition in the apparent magnitude or even the rounding half constant. This remains one possibility. The other possibility is that this AB tension around here is fake, so we have to calibrate the low Z supernova AB value with the value we obtain from the high Z supernova. So we can shift all the red points below by the same value of the 0.043. And then after you do that, you will shift the significance of dark energy from the 73.7 sigma to the 1.6 sigma. And if you further eliminate the CMB data, the significance even below 1 sigma. Okay, this is a very important result. It's the DAISY claim for the dark energy is highly biased by the low Z data in the dark energy survey EFI data. Okay, since the low G supernova is not cannot be trusted, so in the DESI data release 2 paper, they just they just get rid of all the low G supernova in the dark energy survey EFI data. So the significance is decreasing to 2 sigma. Or you can do better. You can get rid of all the supernova data and using only DESI BAO and also CMB. So the significance seems to be 1.3 sigma. Okay, this is a very strong indication for the dark energy. But to be careful that you have to test this consistency between the DESI BAO and also the Planck CMB before you fit to any specific model. So in the lambda CDM model, the CMB and BAO data is not consistent with each other. As you can see that they disagree with the value of the matter fraction. And also, so this is the result is obtained in the lambda CDM model. Even if you use this W0 WA CDM model, so this is the dark energy model they use, you will find that even using their dark energy model, you will find that the CMB constraint for the matter fraction is far away from the BAO and also the BAO and also the supernova. So in this dark energy model, you cannot combine the CMB and also BAO data to claim any deviation from the lambda CDM model. So this claim is questionable. Okay. And even worse, in the W0 WA CDM model, the measure Hubble constant is even smaller than the value we measure using the lambda CDM model. So the Hubble tension is even worse in this dark energy model. Okay, the reason for that is that to solve the Hubble tension at the late universe, you require that the late expansion rate has to be larger than the cosmological constant. So you need a phantom transition from the equilibrium state of dark energy to be higher than -1 into a value that the equilibrium state has to be smaller than -1. But for the DESI results, they prefer the opposite. They prefer the dark energy expansion rates to be first faster than the cosmological constant, but slower than the cosmological constant in the end. So their expansion rate at our current universe is smaller than the cosmological constant. So their measured Hubble constant is even smaller than the lambda CDM model. So these two are in tension. So you cannot solve this Hubble tension in the DESI preferred dark energy model. And even if you can add some early dark energy model in the W0 WA CDM model, as long as you add the truth measurements of Hubble constant as prior in this data in their data combination, you will find that the dark energy significance is reduced in these cases. Okay. Yes. Yeah. This is the deceleration parameter. The negative value is called acceleration. So the less negative value means less acceleration. But to solve the Hubble tension, you need larger acceleration. Yes. Even worse. Yes. Yes. Mm. Yes. 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 Yeah. You're absolutely correct. Yes. So now we are facing the problem that maybe the dark energy interpretation of the DESI result is not correct. So people are shifting the attention to the modified gravity. So here there's two papers to use the EFT model to model the late time dark energy model, and they find that there's a parameter coupling between there's a coupling parameter between the matter content and also the Einstein gravity is non-zero. is non-zero away from the lambda CDM model. So this is the general relativity expectation, but the Daisy results admits a 3 sigma away from the general relativity. So we are expecting some kind of non-minimal couple gravity model to explain this result. So that's too much, but I will show you why. Yeah. Okay. So actually, you know that the Daisy model prefer a phantom transition, and in the single degree of freedom, you cannot have a phantom transition from the general relativity. So you have to use modified gravity to explain this phantom transition. This is one argument. Yeah. Yes. Yes. I forgot to mention. So there's many possibility to explain why there is a omega m difference between different measurements. So you mentioned the other possibility that maybe the dark matter redshaped differently from cold dark matter during the evolution. Yeah, that's the one way. Yeah, but I will show that in the equivalent modified gravity model, you can achieve this picture as a merge phenomenon. So this is one example. In this picture, we admit that Einstein gravity and also a minimal coupled scalar field, and then some standard model contents. But we assume that maybe the dark matter not minimally coupled to gravity, but non-minimally coupled to gravity via a scalar field. So in this way, for example, we have choose this kind of potential. In this way, this scalar field is the chameleon field. It has a people's ritual potential in this shape, but there's a non-minimal coupling between the matter and also the gravity. So this will contribute an extra turn to the effective potential of the chameleon field. So with larger matter density, the minimum point of the effective potential is higher. And we know that the minimum point is the effective cosmological constant. So this means that at the high density region, the effective cosmological constant is higher. It means that in the over density region, it will expand locally faster than the background. So here, to solve the Hubble tension, you only need the local over density to be a percentage over density region. Then the Hubble constant could be larger value measured from the background. So this is the model we considered a few years ago. But in this picture, we can also have a very insight for the recent result of Daisy, because in this model, the dark matter and the dark energy are coupled to each other. They cannot be regarded as a separate fluid. They should be combined together as a unified fluid. If you force to separate these unified fluids into what we call by cold dark matter and whatever left as the dark energy, you will find that the fitted dark energy equation state will cross this phantom crossing, and also the dark matter is not the standard cold dark matter. So in this way, we may explain the result. Okay, let me take the last few minutes to test this model. To actually test this model, so maybe you are not, you may be not much appreciate from this picture, because in the lambda CDM model or in the general relativity, the picture is opposite, because in the general relativity, the empty space is spanned faster than the background. This is the general relativity picture. If this empty space, there's a less matter, it means that there's a larger dark energy, so it will expand locally faster. But in this picture, you need an over density to expand locally faster. So the picture is opposite. To test this picture, we use a very direct way to test the picture. So to test the picture, we can measure the Hubble constant from different samples of the supernova. These supernovae are living in different over density. For example, we have some. Let me skip this part. Here I test this picture by calculating the local environment of each supernova. The local environment of each supernova are living in different over density. So we can select a sample of supernova. They are living in the same over density. Same over density. They don't have to be the same region. They only need to be the same over density. And then you group this kind of supernova in the same over density, and then you fit with the lambda CDM model. You will find the Hubble constant from this group of supernova. We can fit Hubble constant from another group of supernova living in higher density region. Then you will find a Hubble constant at a different region with different over density. I test these results for all the Python pros data, and then I use the matter reconstruction technique from the BOSS survey to calculate the local density of each supernova. But when you calculate the local density of each supernova, you have to assume a certain scale. For example, you are talking about some certain scale average density of that supernova. So here I choose the scale, for example, at 17 megaparsec per edge. Then you can calculate all the local density of each supernova, and then you can group this supernova according to their local over density. Then you can measure the Hubble constant from each group of this supernova. You will find that for the supernova living in the over density region, Hubble constant is higher than the supernova living in the under density region. So this is the result with this bias term from the mass correction of the host galaxies. Even if you without this kind of correction, the result, the trend does not change, but only the overall value of the Hubble constant changes. So then you can fit this slope of this correlation between the Hubble constant and also the local over density of the supernova. You will find a slope. Then you can change a difference scale to calculate the local density density value of the supernova. You can change this value to be 13, 14, 20. You can fit different slope of this correlation. So this is our final result of the slope K with respect to the scale you use to calculate the local density of the Hubble of the supernova environment. You'll find that this slope is initially 0 and then change a little bit to negative value and then all the way to the positive value. This green dashed line is the lambda CDM model prediction. So at a certain scale, this difference is almost 3 sigma. So we detect 3 sigma effect for anything, for any new physics beyond the general relativity. So this is what we call the dead edge zero tension. This is different from the Hubble tension because to see the Hubble tension in this figure, you not only fit the slope but also fit the intercept, and the intercept value characterizes the Hubble tension, but the slope characterizes this dead at zero tension. So in this sense, Hubble tension is a tension at the background, but dead at zero tension is a tension at the perturbability level. And this is a picture what we exactly expect from our model, that the over density region will expand locally faster than the backgrounds, in contrast to the lambda CDM model. So I skip this point. Yeah. All these questions we have considered. All these questions when we. Yes, this is actually a very approximately. Mm, mm, mm. Yeah, how they correct this cosmetic flow in the Python pulse data? They correct, as far as I remember. So the data we use is exactly their release data for the Python pulse. So in this picture, we already consider this cosmic flow correction. Uh, 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 so for each different group of supernova, they expand a different redshift range. Highest is around 2. So in the Python pulse data, their redshift is so in here we only calculate the local over density of the supernova, which intersect with the Bose survey region. So if the region is not surveyed by the Bose, we cannot calculate the local density of this supernova. So we don't calculate this this supernova. We only calculate the intercept sample. Okay. So in the end, okay, sorry. Okay, so in the end, we are facing something that is this fluctuation, the matter fluctuation dependence of effective cosmological constant. So this may help us to reconsider the cosmological constant problem. In the traditional way to think of this cosmological constant problem, we have this vacuum energy at a small scale. And so if you assume the gravity is general relativity and also the Lorentz variance and the conservation of the matter quantum, and then the effective field theory description of this quantum field theory in the curve backgrounds, then you can see that it defines as this effective cosmological constant, which is the Bayer part plus this EFT part. But on the other hand, what we measure at the large scale for the dark energy has assumed the cosmological principle that allows us to use FRW matrix. And with that matrix, we can measure the observed cosmological constant to be very small number. But these two parameters are defined at two separate scales. So this is the vacuum energy at the local scale, but this is the observed dark energy at the large scale. Only when you regarding these two as the same quantity, you are facing this fine-tuning problem for the Bayer cosmological constant. But these two parameters cannot be the same because at local scale, you cannot use this cosmological principle to use FRW metric at the local scale. So at the very local scale, the spacetime should be highly inhomogeneous. You cannot use this FRW metric at the local scale to infer these two values to be the same. So by definition, there's no cosmological constant problem if you think that the cosmological constant is a scale-dependent quantity. So this message I'm trying to convey in this talk. So let me summarize this talk. So first of all, there's indeed a Hubble tension from the first few slides. The second is that the early solution cannot, the early solution alone cannot solve this Hubble tension and also the SA tension simultaneously. And also the late-time solution are strongly constrained by the inverse distance ladder. And there's an AB tension between the low G and the dark energy surface supernova that bias the DC implication for the dark energy. And also there's an omega M tension between the Planck CMB and the DC BLO data that also bias our hint for the dark energy from the DC. And also there's a data zero tension in the local scale universe, even for the lambda CDM. So this has inferred some signature beyond the general relativity, which gave us a non-minimal coupling matter with the gravity. So this is the talk today. Thank you very much. And I'm happy to take questions now. Thank you.
Are there any questions?
Yes. You have something like Einstein's equation for your modified variable. Then you can bring some parts to the left hand equation on the right hand side of the equation. Oh, so which part is at the right hand side? Yes. Yeah, this is kind of a missed scenario. It's kind of say it's purely modify gravity or modify the matter contents. It's a mystery. Hmm. Yeah, yeah, yeah. But maybe yeah. Okay, okay. I admit that maybe I oversell this idea. Yeah. Mhm. No, I don't question homogeneity. No, no, I didn't question any observed homogeneity. No, the background is still homogeneous, but only the local scale environment of the supernova. That scale is not as large as homogeneity scale. Yes. The scale is below. Sorry, the scale should around this scale is not reaching the homogeneity scale. No, 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 no. In the end, it will come back to the homogeneity result. Only at this scale, you show some deviation. Yes. It's around, like say, 17 megaparsec per inch. Yes. 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 So basically, the determination of the quantum sequences for supercluster that we can see are accelerating in comes. That there is some idea that they report. So by by observation, we do observe some KBC void and also the Great Wall, but it's not statistically significant because if you only count the galaxy number, is already become the homogeneity around 100% megaparsec. Yeah. 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 Yes. Uh, so what we do, I admit that for that supercluster, you do have this attraction to the great attractor, but you have to remember that they still getting far away, but with a tendency to attract to this great attractor. Yeah, after you eliminate all the corrections from the local environment, it seems to attract to the point. But my result does not require that for this specific reason, for this specific location is homogeneous or inhomogeneous. I do the statistical analysis for all the supernova points around us, not just our local point. Yeah. Yeah. Yes.
What if you data?
No, I didn't mean it. You can do that. You can do that. Yes. Yeah, at the higher redshift, the matter over density is in overall decreasing. So that's why you measure the Hubble constant using the data from higher redshift. You measure the Hubble constant very even closer to the background value because the over density is decreasing when we go to the higher redshift. Yeah. Yeah, maybe we can discuss this specifically. Yeah. Okay. Thank you. Bye.